Two styrofoam balls with the same mass, m equals 9.0 times 10 to the minus 8th kilograms, and the same positive charge q, are suspended from the same point by insulating threads of length L equals 0.98 meters. The separation of the balls is 0.020 meters. What is the charge q? So here we know that these two spheres essentially are electrically charged with a certain amount of charge, the same charge. Because they're both positively charged, we know that these spheres will repel each other. Using that information and using a little bit of trigonometry, I think, we're going to be able to determine how much charge is on each sphere. So to do that, let's start off with our own sketch. So I am going to redraw the two spheres. So here is one sphere, here is the other one. I'll indicate that these spheres each have charge q, so q, q. I am going to label my own values for q, just following good problem-solving methodology. We don't know what the value of q is, so I'll just leave that as an unknown. We do know the length of each string. I am going to label that in our diagram as capital L. So the length of each string is 0.98 meters. We do know the separation distance between the two spheres. So that separation distance is d. This is grossly exaggerated and definitely not to scale. D is equal to 0.020 meters. We know each ball has a mass of m equals 9.0 times 10 to the minus 8 kilograms. Using this information, again, we have to solve for q. So how I'm going to do that is I'm going to take one of these spheres, at least. I might need both of them, but for now, I'm going to start off with one of them and analyze all of the forces acting on that sphere, because we do know one thing that connects these two spheres together. Since they are charged particles, we know that the Coulomb force between them is equal to, in magnitude, k times the product of the two charges divided by the distance between those charges squared. Well, in our problem, the charges both have charge capital Q, so this will be Q squared over the distance between the charges is d. So this connects us. This force right here has Q in it. Since these are both positively charged spheres, they're going to repel each other electrically through the Coulomb force. So I'll illustrate that on each particle, and I will go ahead and label these forces F sub E. Now, each particle has a mass, which means there is a force of gravity on each particle, which I will just label that F sub G, and we know that is the mass of each particle times the free fall acceleration of gravity. There is also a tension acting on each sphere directed along the string. So I will label that F sub T for the force of tension. Now that I've identified all of the forces acting on our sphere, at least on the sphere on the left, I'm going to transfer that to a free body diagram. So remember, a free body diagram is a diagram that illustrates the forces acting on a single object or a single system. So this is going to be representative of the left sphere. The sphere is represented in the middle, and I am just going to transfer those forces to my free body diagram. So we have the tension force coming off at an angle. I will call that F sub t. We have the weight. We know the weight is equal to mg. And then we have the Coulomb force acting on the left sphere. That Coulomb force is equal to F sub e. Now, we know that the sphere is in equilibrium, so that means it's not accelerating. So since we have a relationship of forces here, let's go ahead and use this information and use Newton's second law to help us use the relationship of these forces to find the charge Q. I'm going to use Newton's second law in its component form. By using it in its component form, that will give me two equations. One equation for the x-axis, one equation for the y-axis. So in order to do that, I'm going to need to break up my tension force into its components. So I will just call this angle an angle theta. Maybe I'll call it theta t to associate it with the tension. That angle theta has an x component, and that force of tension has a y component. So I will call this component force of tension in the y direction, this component force of tension in the x direction. So just quickly redrawing our free body diagram, I have our two axes. We have the y component of the tension force. We have the x component of the tension force. We have the weight of the object. And we have the Coulomb force acting on that sphere. So again, this corresponds to the left sphere. Now you're wondering, why are we drawing the free body diagram? Why do we have to do this? One, it's good problem-solving technique. Think of it as if you're building a house. You want to assemble all of your tools together before you build the house. The tools we have are sketches, and a very important sketch is a free body diagram, because each axis is the graphical representation of an equation. This free body diagram I drew on the right represents the component form of Newton's second law. All I have to do is sum up the forces along a particular axis and let it be equal to the product of the mass and the acceleration on that axis. So for the x-axis, and I see I have a little typo here on the force of tension along the x direction. That should be, I had a subscript y, but that should have really been a subscript x on that one. Okay, so looking at the sum of the forces in the x direction for our sphere, all we have to do is sum up the forces along that axis. That's the force of tension in the x direction minus the Coulomb force. That is equal to the mass of our sphere times the acceleration in the x direction. Since our sphere is in equilibrium, there is no acceleration. The acceleration is 0. So this gives us a first relationship. The force of tension in the x direction minus the Coulomb force between the spheres is equal to 0. Well, let's drill this down, because remember, the Coulomb force contains information about our charge. So let's go ahead and work with this a little bit more. If we go back to our free body diagram, we see that the force of tension in the x direction is equivalent to the adjacent side of a right triangle where the components of our tension correspond to the legs of the right triangle. So that means that our x component of tension is equal to the magnitude of tension times the cosine of the angle that the tension makes with the x-axis. So coming back to our Newton's second law, I could replace the x component of, of the force of tension with the magnitude of tension times the cosine, the angle of the tension, the angle that the tension makes with the x-axis, minus the Coulomb force. Well, remember the Coulomb force is K, the Coulomb constant, times the charges squared divided by the distance squared between them. And that is equal to 0. So let's see what we have here. Here we have a relationship between the charges and the tension force. What we don't know is we don't know the force of tension, nor do we know the angle that the string makes with the x-axis. However, we have enough information to determine that. We have enough information to determine the angle, and we have enough information to determine the force of tension. So for now, I will just kind of put that aside. I'll go ahead and call this equation 1. I will then turn to the y component to see what information that gives us. So looking at our free body diagram, I see that our Newton's second law in the y direction is equal to the y component of tension minus the weight of that sphere is equal to mass times the acceleration in the y direction. But again, our sphere is in equilibrium, so it is not accelerating. So this means that the component of tension in the y direction minus the weight of a sphere is equal to 0. And similarly, using trigonometry, the tension force in the y direction is equal to the magnitude of tension times the sine of the angle the string makes with the x-axis minus mass times gravity is equal to 0. So here is another equation we could use. Notice we have 2 equations and 3 unknowns. The unknowns are the magnitude of the tension force, the angle the string makes with the x-axis, and the magnitude of charge Q. So there's a couple of different ways we could proceed on this algebraically. We have enough information to solve for the angle because we have 2 sides of a right triangle. The 2 sides of the right triangle just comes from the string and the ball, and I'll illustrate that right here. So if we look at this scenario, remember the distance between the 2 balls is a distance d. If I create a right triangle from that, where we know the leg adjacent to the angle, that leg is d over 2. The hypotenuse is L. This gives us enough information to solve for the angle. And in fact, maybe we'll need this, maybe we won't, but this also gives us enough information to solve for that side. I know from Pythagorean's theorem, hey Wiley, That's my dog Wiley. He wants to answer for us. And he said, Mel, that opposite side from Pythagorean's theorem is equal to, well, let's see. Pythagorean's theorem is L squared is equal to D over 2 squared. And let's just call that opposite side. I'll just say that opposite side is a length A. So we'll say A squared. This at least says that we have enough information for all of our sides. Maybe it'll come in handy later. I don't know. But trigonometry is a very, very useful tool for us. Even though there's a couple of ways we could solve for this algebraically, I want us to practice one technique of solution. Let's solve for variables. Let's solve this system of two equations by eliminating one of the unknowns. We don't really need T, the tension, to solve for this problem. So let's see if we could eliminate it. Now, I recognize something. I recognize that tension can be isolated in both equations. So whenever you're able to isolate the same unknown in two different equations, you could rewrite those equations so you could divide one equation into the other equation, and that'll eliminate that unknown. When you get used to this, this can often save you at least a couple of steps of calculation. So what I'm going to do is I'm going to take equation 2. I am going to isolate the term with tension in it on the left side of the equation. I'm going to take equation 1 and do the same thing. Now that I have the tension terms isolated, I am now going to divide the second equation that I just wrote into the first equation. I'm going to just illustrate that just by putting this dividing line between both sides, dividing one equation into another. So if you look at the left side, notice how that tension in the numerator cancels with the tension in the denominator. That's awesome. So this allows us to reduce our unknowns from 3 unknowns to just 2 unknowns without even having to solve for one of those unknowns, which is tension. So this is what we have so far. The tangent of the angle between the string and the x-axis is equal to the distance between the charges squared times the weight of one of those charges divided by k times q squared. So the last unknown we really need to deal with is that angle, tangent of theta t. So let's deal with that angle. We could deal with that angle by going back to our right triangle. Let me actually redraw this right triangle just so it's a little bit cleaner. This side is d over 2, this side is a, this side is L. Here is our angle. You know from trigonometry that the tangent of that angle is equal to the opposite side over the adjacent side. Oh, and you know what? Earlier, we solved for the square of that opposite side. So we could write that opposite side as L squared minus d over 2 squared over d over 2. Well, we could clean this up a little bit. We could say that the tangent of our angle is equal to the square root of L squared minus d squared over 4, and that is going to be the square root of 2 comes to the denominator. Comes to the numerator. D stays in the denominator. So what does that leave us with? Well, remember we said the tangent of theta t is equal to d squared mg over kq squared. Tangent of theta t, we just found, is equal to 2 times the square root of L squared minus D squared over 4 over D, and that is equal to D squared mg over KQ squared. So let's solve for Q. I'm going to just flip both sides of the equation. I am now going to isolate Q. And now that I've isolated Q, we just have to take the square root of both sides. So that is Q equals the square root of D cubed mg, and that is over 2k times the square root of L squared minus D squared over 4. So this is the candidate for our answer for Q. Before I plug in numbers, I want to do a quick unit check. Now, the unit check will help me determine if I made any mistakes. If I made a mistake, if my units don't check out, I know I made a mistake somewhere. The mistake could be in just the unit check itself. But most of the time, the mistake is in my algebra. I might have forgot a squared. I might have used one symbol when I needed to use another. So the unit check will help me determine that. So how I'm going to do the unit check is I'm going to just look at the units of each of these quantities and see if it works out. So the unit of charge Q on the left is the coulomb. Now let's look at the square root. So I'm going to just write the square root as a power to the 1/2. So in that square root, I have a D cubed. D is a distance. So distance has units of meters. So that's a meter cubed. Mass has units of a kilogram. So I'm just looking at each of these quantities in turn. So D has units of meter cubed. Mass has units of kilogram. G has units of meters per second squared. So I'll put that meters per second squared here. Divided by 2. So constants like 2 are unitless, so you don't need to include that in your unit check. K has the units of Newton meters squared per coulomb squared. You should go ahead and double check that. And then I know I have a square root of distances squared. So L squared is a meter squared. D squared is a meter squared. Now, I'm not going to actually subtract them. All I really care about is both terms have the same units. The units are a meter squared. So I know under the square root, we have units of a meter squared. Now let's simplify to see what our final units are going to be, and we are looking for the final units to be coulombs. So I see that in the denominator, notice I have a meter squared here and a meter squared here. The square root of a meter squared is a meter. So this meter times this meter is a meter cubed. That meter cubed cancels with a meter cubed in the numerator. You know that 1 Newton is equal to a kilogram meter per second squared. So I have a Newton in the denominator. That cancels with a kilogram meter per second squared in the numerator. I am left with, in the denominator, a 1 over a coulomb squared to the 1/2. You flip that, and notice we end up with units of coulombs after doing all of that. So our units checked. Now that I did our unit check, I'm going to go ahead and plug in the numbers. And I'm really glad I didn't plug in numbers first, because if I made a mistake, I would have had to erase all of that work. But now I could be pretty confident that my value is going to work out. So this is, again, d cubed mg over 2k square root of L squared minus d squared over 4, and that's all underneath the square root. So let's go ahead. I'll start off by writing the denominator. So that is 2 times 8.99 times 10 to the 9th Newton meter squared per coulomb squared. We already know the units will work out, but I still like writing units here because it just gives me another opportunity to check myself. So then this is now times, and that's going to be a square root, so I'll just write it as a power of 1/2, L squared. So L is the length of the string. We know the length of the string is 0.98 meters. So 0.98 meters quantity squared minus the distance between the charges. Well, the distance between the charges, we know they are separated by 0.020 meters. And that quantity is squared, and that quantity is divided by 4, and all of this is a square root. And then the numerator of this expression is the distance cubed between those quantities. So 0.98 meters quantity cubed times the mass of a sphere. So we know that the mass of a sphere is 9 times 10 to the minus 8th kilograms. So 9.0 times 10 to the minus 8th kilograms times the acceleration of gravity. And all of this is underneath the square root. So this is another opportunity to do a unit check. And we will just quickly do this unit check. So I see I have a meter squared meter. I know these will cancel with that. I know this Newton will cancel with the kilogram meters per second squared. I'm left with a coulomb for my unit, just like we did before. So I am ready to plug this into my calculator. And I get a charge to two significant figures to be 6.9 times 10 to the minus 9, which is the same thing as 6.9 nanocoulombs. So let's quickly recap what we did. We started off with a sketch. We needed to find the charge, so we knew that the thing that connected us with the thing that connected the two objects is the Coulomb force between them. So that led us to use Newton's laws, and in order to use Newton's laws, we drew a couple of free body diagrams. The free body diagrams gave us two equations, the component form of Newton's laws. So we have the x component of the force acting on one of the spheres and the y component. So that gave us two equations. Now the trigonometry naturally suggested itself because we were given a length of the string and the distance between the spheres. So that led us to use trigonometry to come up with the third equation to give us an expression for tangent. Now, using a little bit of algebra, we chose to solve this by using the elimination method to eliminate the variable of tension. And a little bit of algebra later, followed by a unit check, led us to an answer of 6.9 nanocoulombs for the amount of charge that must be on each of those spheres in order to cause the separation that they have.